So, okay, all right. So, I want to first of all to acknowledge my uh, somewhat long list of collaborators: Virna Meccia, Roberta D'Agostino, Federico Fabiano, Paolo Davini, Sarah Larson, Jos von Handerberg, and Susanna Corti. And today I'm presenting some work that we did looking at the impacts of a weekend AMOC using the ECR3 climate model. So first of all, I wanted to start about talking about some well-known impacts of the AMOC on the mean climate to warm up a little bit. So as you can see from this observational estimate taken from September 2019, we know that there is an interhemispheric imbalance in the ocean heat transport, meaning that on average, the ocean transport more heat into the northern hemisphere compared to the southern hemisphere. And if we look at the breakdown by basins, we see that this is because of the Atlantic basin, in which the oceanic heat transport is always towards the northern hemisphere. This is because of the AMOC, and this imbalance in northward heat transport by the AMOC has two main consequences on the global mean climate. So, or at least it's thought to be due to the AMOC transport. There are also other theories, but nevertheless, this other schematic is taken from Frears et al. 2013, and shows that in the northern hemisphere, the climate is slightly warmer than the southern hemisphere, and this is again thought to be caused by the heat imbalance, the ocean heat transport imbalance due to the AMOC. And because the northern hemisphere is slightly warmer than the southern hemisphere, the effect of the AMOC is also thought to have an impact on the tropical rain belt, namely the Intertropical Convergence Zone, the ITCZ, which is thought to be shifted slightly above the equator at about 5 degrees north in the zonal mean because of the ocean heat transport by the AMOC. So mainly because of paleoclimate evidence for example, during the Oscar event, in which the climate has cooled by a lot, and that this is thought to be associated with states in which the AMOC was significantly weakened or even shut down. Many simulations with global climate models have been carried out throughout the years to understand the impacts of a weakened AMOC on the global climate. And there are a few studies actually, but I singled out these two because they were actually 10 years apart. So Zhang and Delwar 2005 was one of the first in the early 2000s to perform this kind of simulations. And Jackson et al. 2015 is also one of the most recent in which an abrupt weakening of the AMOC was imposed through the water housing protocol. So there are also some well-known simulated impacts of a weakened AMOC on the global climate, and these 4 panels show it. So the top 2 panels both show that in these 2 climate models, as in many others, the consequence of an abruptly shut down AMOC or significantly weakened is that there is a global mean surface temperature cooling in the northern hemisphere, which is only slightly compensated by warming in the southern hemisphere, but overall, over the globe, the climate cools. And also, as a consequence of a weakened AMOC, you can see in both studies, even though they use different colors for anomalies, but you can see there is a southward shift in the zonal mean ITCZ as a consequence of the cooling in the northern hemisphere. Because we in the study focused in the winter season, I decided to show some other previous studies that focused in winter, and this one is taken from Williams et al. 2012, and shows here a focus on the Euro-Atlantic region, which is also the focus in our study. of the mean wind response. This is on the left. The panel on the left shows the wind speed at 850 hectopascals. These are maps of anomalies of a water hosing experiment compared to a control climate. And so this figure here on the left shows that, sorry, I'm gonna go back. This figure here on the left shows that the jet stream is enhanced and slightly shifted eastward towards the European continent. Instead, this panel here on the right is that together with an enhanced jet stream, there is also an enhanced storage track response when the AMOC is weakened. See, these other figures are again taken from Jackson et al. 2015 for the winter season. They also focus in their study both on global mean climate change, but in particular over the European continent as well. And these figures, I thought they were particularly interesting because the figure on the left shows that even though the climate is colder due to a weakened AMOC, there are some changes in atmospheric circulation that result in actually relative warming over the European continent. This is happening because even though the climate is colder everywhere, the ocean is still warmer than the land. So the land cools more than the ocean. So in winter, the effect of thermal advection from the ocean are still to warm land in comparison to the water. And this other figure on the right shows the relative precipitation anomaly in the JF. And also here, I thought this was interesting because it's consistent with some of our results that's showing that even though overall the climate is drier, there are some regions that experience a relative increase in precipitation anomalies. And in their study in 2015, Jackson et al. Argued that these are this increase in precipitation anomalies were associated with this increased storm tract activity, which was also found in previous studies. So coming to our study, so I said there is some previous work that looked at climatic impacts of a weakened AMOC, but we thought there were still some unknowns about these impacts, especially on daily timescales. So we ran some of our own simulations with ECR3, and we focused especially in the Euro-Atlantic region in Bora winter. And as you will see from our results, many of them are based on data taken from daily output, differently from most of the previous studies that instead looked at seasonal mean or long-term means. And in particular, we looked at precipitation, weather regimes, and temperature impact in this region. So as I already extensively mentioned, we performed water hosing experiments with ECR3. We used the model in the standard CMIP6 configuration, which corresponds to resolution of the atmosphere about 100 kilometers and of the ocean about 80. And we run two experiments. So the first one is a control experiment, and I'm gonna refer to this as the control throughout the rest of the talk. And this is run in pre-industrial control conditions for 150 years. So this is basically the same as the CMIP6. And in the control experiment, all the climate variations are internally driven, since the external forcing is kept fixed at the representative year 1850, representative of the conditions before the industrial revolutions. And then to compare with this control experiment, we run the water hosing experiment, and we do it by adding 0.3 squirt drops of fresh water in the area that is highlighted here in this figure in cyan. And we do this for 140 years, and then we leave the model to freely evolve. This is what we obtain when we look at the AMOC response to the water hosing. So this these panels here on the right show the AMOC string function. In the top panel is the control simulation, and the bottom panel is the string function taken from the water hosing when the AMOC is at its weakest point. So over the 60 years that are highlighted here in this time series on the left. And so as expected, as a result of the water hosing, the string function is much reduced in the water hosing experiment. And instead, if we look at the time series, and this is the AMOC index computed as the maximum of the string function between 25.5 north and 27.7 north, below 500 meters. So you can see in the control simulation, there is a mean AMOC value about 17.66 Sverdrups. Instead, in the water hosing experiment, as a result of the water hosing, you see that the AMOC steadily declines until it reaches its minimum at 140 years, at which point, as I mentioned, we stop the hosing. And as a result of stopping the hosing, that in this model, the AMOC recovers within a few decades. Oh, it shows like it's recovering to its original strength quite steadily. So I'm going to point out a couple more things here in this figure. So the first one is that in this model, ECR3, as many of you probably know, there are these centennial fluctuations in the strength of the AMOC, which are seen here in this figure. And so in this study, we account for these fluctuations by taking the means over a full cycle, basically, so that our comparison with the water host climate are not affected by this oscillation. And we also have a paper led by Vietnamese et al. In 2022, which has been recently accepted in Climate Dynamics, in which we provide some mechanisms for explaining these unforced centennial oscillations in ECR3. I'm just going to note that although this is a problem in this model, and these oscillations may, they may affect some of our results, we do some statistical tests, of course, and we also note that the amplitude of these oscillations, which was estimated by Betch et al. To be 3 Sverdrups, is much less than the average decline of the AMOC over the considered period here of 60 years, which is more than half the AMOC of the original of the pre-industrial control experiment. So in the rest of this talk, I'm going to show you results of averages or statistics taken between the 60 years in which the AMOC is weakened, which are highlighted here, and the full averages and statistics of the full integration of our control experiment. So moving on, first of all, we wanted to kind of look at the mean climate response and to see whether it was in agreement with previous studies and generally speaking, how the ECR3 model responded to water hosing compared to previous modeling experiments. So these figures present an overview of changes in the annual mean, and has anticipated and as expected, the global mean climate cools, and especially this is seen in the northern hemisphere, while the southern hemisphere presents a slight warming that only very partially compensates for the overall global cooling. And as in previous studies, we see a general drying over the northern hemisphere and a southward shift in the zonal mean ITCZ. This is seen here in the panel at the bottom left, but is even better seen in the panel on the bottom right that shows the zonal mean precipitation in the control in black, and in the hosing experiment where you see the southward shift as a negative anomaly, where typically the ITCZ sits in the northern hemisphere, and you can see its shifts is an anomaly, is positive peak from being in the northern hemisphere to the southern hemisphere. And together with these global changes, we also find a change in the Hadley cell, which is consistent with the southward shift of the ITCZ. As I mentioned at the beginning, we are in the study mainly interested in the Euro-Atlantic region in DJFM, so in winter. And we look specifically at precipitation impacts. As you can see, overall, the climate dries, but there are some regions in this, you can already kind of see in this map in which the precipitation anomalies are not drying, but are actually slightly wettening. And this was also consistent with the paper by Jackson et al., which I showed earlier, in which they used a higher resolution model. And they also found regions where precipitation showed to increase a little bit, even though the climate was overall drier. So we wanted to look into more detail of daily statistics of precipitation change. So we computed the change in the number of wet days anomalies by looking at very rainy day. And by very rainy day, I mean the days that exceed the 75th percentile precipitation anomalies computed from the control run. So these two figures show, so the first one on the top shows, first of all, the 75th percentile precipitation anomalies computed from the control run. These are units of millimeters per day. And then the figure on the bottom shows the difference in the number of days above the 75th percentile of the control simulation, but it's the difference of this number in the water housing minus the control experiment. So this figure, which highlights more of the daily anomalies compared to the seasonal mean changes, does show, consistent with the paper by Jackson et al. In 2015, an actual increase in very rainy days in some regions. We were kind of intrigued by this heterogeneous precipitation change, and we wanted to go more into details on mechanisms of precipitation anomalies, and we wanted to answer these basic two questions. So previous studies, and also what one could think about the impacts of AMOC weakening is that, so overall the climate is colder, so the atmosphere should hold less moisture due to the Clausius-Clapeyron constraint. So is the overall drying a consequence of the Clausius-Clapeyron constraint due to thermodynamic processes? Because the atmosphere is overall colder, and so it should hold less moisture. And then instead, are these wet anomalies that we see in the daily statistics, are they instead related to changes in storm activity? So to address this question and to be a little more quantitative about mechanisms of precipitation change, we computed the moisture budget analysis. And this moisture budget analysis also has some history in hydrology and hydrological changes studies. And in this, we follow the framework in D'Agostino and Lionello 2020, which is based on the earlier paper of Richard Seeger and co-authors. And so the moisture budget analysis is attempts to explain the net precipitation change, defined as precipitation minus evaporation, due to, and split into contributions due to the mean flow and transient flow. So this figure here shows the net precipitation. So before I showed the P minus E, so just the precipitation, while this one is the P minus E change. And you see in these figures some represented regions, for which I'm going to show budgets later on. And these regions were chosen because they have over land, they have same sign of precipitation anomalies and seem to be coherent in terms of, spatially coherent in terms of mechanisms of precipitation change. So as I said, the moisture budget analysis splits the contributions due to the mean flow and to the transient flow. transient flow means that these are submonthly timescales anomalies. Hold on a second. I apologize for the cough. So, Jose, you can further expand this equation, and so you can get contributions that are just due to the change in the mean flow, and changes due just to thermodynamic processes. Just that means changes in the moisture, and then contributions due to the transient flow. So this would be nonlinear eddies and so transient eddies and nonlinear terms, and also a term that is due to surface processes. So overall, you can write the budget, the change in moisture budget, has a contribution of 4 terms. The change in the moisture budget that is just due to thermodynamic processes. So if you look at these equations, basically this is you see that the only thing changing here is the moisture, the vertically integrated moisture, while the mean flow is taken from the control run. Then there is a second term that is that just due to dynamic changes. So in this case, the moisture is taken from the control, but you look at changes that are just due to the mean flow. And then there are these 2 terms, the transient eddies and nonlinear terms, that which we in this study we incorporate together because we overall find that the nonlinear term is very small. So we can put it together with the transient eddies when looking at the results. And so I'm going to note here that the transient eddies and nonlinearities are due to timescales less than monthly, so sub-monthly timescales, but differently from the thermodynamic and dynamic term. Here, because these are computed as covariances, the changes in moisture and the mean flow and the flow cannot be separated. So the transient eddies and nonlinear term will have contributions from both thermodynamic and dynamic processes, differently from the monthly timescales. And then the last one is the surface term, which is calculated as a residual here. So when we apply this framework to our experiments, this is what we find. And so just to recap, these are the 4 contributions to the change in net precipitation of the water housing minus the control. And so overall, I'm going to point here to the 2 main features. So while we hypothesized that the mean climate is cooler, and therefore the Clausius-Clapeyron should bring overall drier condition, we actually see in the thermodynamic term, which should encapsulate this concept, that the contribution is quite scattered over land. And so it's not simply the thermodynamic term that dries land in a weakened AMOC climate, but it is actually, so the overall drying, the biggest contribution comes from the transient eddies and nonlinear term. So this was the first, I guess, surprise here. And the second one is that, perhaps less surprising, is that they said the wet anomalies that we saw in some parts of Northwestern Europe, it seems to be associated with the dynamic term. So as I promised, here are this is the balance for some selected regions. So you can see Northwestern Europe in this box. Indeed, the positive, so the dynamic term would overall contribute to wet anomalies in this region. So the positive delta P minus E here is mainly contributed by the dynamic term. Instead, in the other 2 regions, you see that while the dynamic term in Northeastern Europe would provide, again, a slight wet contribution, is mainly the transient eddies terms, and in this case also the thermodynamic term that contributes to less precipitation anomalies. And we can conclude the same for the southwestern Europe, where although here the thermodynamic term instead it would provide wetter condition, and instead the dynamic term provides drying condition. So this was this was an interesting result, but we still found that we needed to connect it back to changes in large-scale atmospheric circulation and storm tracks to be able to better understand mechanisms of precipitation change. One thing that clearly emerged from this analysis, though, was that the moisture budget framework highlights the fact that it's not simply a Clausius-Clapeyron consequence of thermodynamic processes that precipitation overall decreases over Europe, but is actually an indirect effect through the transit eddies term. So here I'm showing, I'm focused here again on the dynamic term. Sorry. So the dynamic term, as we discussed, provides a wettering contribution over Northwestern Europe and a drying over Southern Europe. And if we look at the change in the zonal wind speed at 150 hectopascals, we see that this is consistent with the changes in the dynamic term. Sorry. So similar to previous studies, we also find that the jet stream is enhanced and is shows a eastward displacement. So the changes in the jet stream are consistent with the wettering of Northwestern Europe. Then looking better at the transit eddies term, we compute the storm tracks, which are computed, which are shown here, the bottom right. So this is actually interesting because we thought, that because the climate is drier over Europe, then you would expect less storms. But what is actually happening is that storm tracks are enhanced also over Europe. And so this means that the contribution of the storm tracks is to dry land, because even though there are more storms, they are drier. So it's the moisture availability, or the lack of moisture availability in the atmosphere, which is actually providing a drying contribution over land. So to summarize, the increased number of wet days is due to a competition between an enhanced mid-latitude jet, which on its own brings wetter conditions over Northwestern Europe. But there's also the fact that there are more storms, but they are drier. So the fact that they are drier overall contributes to drying Europe. So even after this analysis, we were left a little unsatisfied with this explanation. And we looked at possible daily atmospheric circulation anomalies that could lead to the increase in the number of wet days over Northwestern Europe and this drying over Southern Europe. So we computed weather regimes and then associated changes in atmospheric circulation patterns of weather regimes with precipitation anomalies. To compute weather regimes, we followed the methods that are explained in much more detail in Fabiano et al. 2020. And so just to go through them very quickly, I'm going to explain how we did it practically. So we took daily geopotential height anomalies at 500 hectopascals. And then we first computed a reduced dimensionality space of 4 UFs in the control simulation, which explains about 55% of the variance. And then we applied the k-means clustering algorithm on the four principal components associated with the first 4 UFs to derive 4 cluster centroids. And then we assign each day in the control simulation to one of the clusters based on the Euclidean distance. So we obtained a data set, basically, in which each day of our simulation is assigned to one of the clusters that are representative of the 4 more dominant weather regimes. And finally, we obtained maps of weather regimes, computing composites of this Z500 anomalies. And weather regimes in the holding experiment are computed using the centroids computed from the control run to be consistent, to be able to make a consistent comparison with the control simulation. This is what the weather regimes look like in the control simulation. And I'm gonna remind you that we are looking at the winter season. So these are the 4 canonical weather regimes in winter that are also found in reanalysis and other previous studies that examined pre-industrial control simulations and historical simulations as well. So the first, the more dominant weather regimes are the top left is the NAO positive phase, and the bottom left is the NAO negative phase. And then on top right is the Scandinavian blocking, and bottom right is Atlantic ridge. And these percentages that you see near each of the weather regimes are the fraction, so the average number of days that fall within each weather regime across the entire control simulation. So you see that most of the time there is a NAO positive phase. There are NAO positive phase events, but I would say that these are quite equally distributed among the 4 weather regimes, or at least they are compared to the water hosing simulation, in which instead we see a major increase in the number of NAO positive events. And as you can see here from this box plots that show the frequency distribution differences between the the frequency distributions in the control simulations and the water housing. So you see that while all the other weather regimes, the frequency of occurrence decreases, in the NAO positive goes from being about 26% to more than 40% frequency of occurrence. Not only the frequency of occurrence increases, but also the persistence in each of the persistence in the NAO positive phase increases in the water housing, as you can see here in the panel on the top left. Instead, consistent with the previous plot, the persistence of the other weather regimes decreases. So finally, as promised, then we went back to associate with these changes in weather regimes with changes in precipitation anomalies. So these are composites of precipitation anomalies for each computed for each days in the NAO positive phase for the control simulation. And for the control simulation, you basically obtain what you would expect from precipitation anomalies associated with the NAO positive phase, which means enhanced precipitation over Northern Europe and drier conditions over Southern Europe. And instead here on the right, these are anomalies calculated with respect to the control climatology. And you see that with respect to the control climatology, you do see an overall drying as expected from the fact that the climate is overall drier. But you do see that associated with an increase in the number of NAO plus day, you see enhanced wet anomalies over Northwestern Europe, where we found there was an increase in the statistics of daily wet days, and also a drying over Southern Europe. So for the first part, conclusions, we examined the impacts of a weakened AMOC on precipitation in winter in the Euro-Atlantic region. To do so, we conducted water housing experiments with the ECR3 climate model. And although overall the Euro-Atlantic region dries, some regions in Northwestern Europe experience wetter days. And we found the mechanisms of these changes in precipitation and found that large-scale atmospheric circulations are the major cause of these changes. So we found that enhanced and more central jet stream promotes wetter conditions, and instead an increase in the frequency of NAO positive days and drier storms explained the drying over continental Europe and drying southern Europe. Instead, the increase in the frequency of the NAO positive days enhanced precipitation in northwestern Europe and enhanced precipitation in Western Europe, and instead promoted drier conditions over continental and southern Europe. So the results that I showed until now are currently under review at Climate Dynamics, and if you're further interested, put a link of the